Bismillahirrahmanirrahim. My dear students and audience, Assalamu alaikum. In this video, we will talk about basic matrix algebra for animal breeding. So, a matrix is a rectangular array set in rows and columns. For example, we have a matrix H here. It has 2 rows and 3 columns. So, its order will be 2 into 3. Order is equal to number of rows multiplied by number of columns. What is a scalar? It is a matrix consisting of single row and single column, and its order will be 1 into 1. A row vector is a matrix having single row, so it would have one row but many columns. Its order is 1 into 3. If we have a C column, it has one row and 3 columns. A column vector would have a single column. So G is a column vector. It has only one column, though it has 3 rows, so its order would be 3 into 1. And a square matrix is a matrix having equal number of rows and columns. It has 2 rows and 2 columns, S, and its order is 2 into 2. 5 and 9 are diagonal elements of this matrix, and 7 and 3 are off-diagonal elements. So this is a square matrix. Diagonal matrix is a square matrix having 0 for all of its off-diagonal elements. These are diagonal matrix. It has non-zero elements along the diagonal, and everything besides it is 0. Identity matrix is a matrix having 1 for all of its diagonal elements. So it is a diagonal matrix, and its diagonal elements are 1. It is identity matrix. A triangular matrix, a square matrix with all elements above or below the diagonal as 0. Uh, uh, so if elements above the diagonal are 0, it is called lower triangular. If below the diagonal are 0, it is called upper triangular. We have L matrix, which is lower triangular matrix. Everything above diagonal is 0. Similarly, U is upper triangular matrix. Everything below diagonal is 0. Symmetric matrix is a matrix, square matrix with elements above the diagonal equal to the corresponding elements below the diagonal. So S is a symmetric matrix. It has diagonal elements 9, 7, 10, and its off diagonal elements are corresponding -4 above, -4 below, 0 here, 0 here. So S12 is equal to S21 is equal to -4. Similarly, S13 is equal to S31, which is equal to 0. Similarly, S23 is equal to S32 is equal to 2. It's very useful matrix in animal breeding. Transpose of a matrix. A transpose matrix is a matrix whose elements ji elements are equal to ij elements of the original matrix. So we have A matrix here with 2 columns and 3 rows, and we have A prime which has 3 rows, 3 columns and 2 rows. So rows of A prime are the columns of A, and columns of A prime are rows of A. So addition and subtraction of matrices is only possible if they have same number of rows and columns. X and Y, they have same number of rows and columns. So X plus Y is possible. Similarly, X minus Y is possible. Matrix multiplication is a little bit tricky. Two matrices can only be multiplied only if the number of columns in the first matrix is equal to number of rows in the second matrix. So we call it the matrices are conformable for multiplication. For example, A has 3 rows and 3 columns, and B has 3 rows. So these are conformable, and C is the product of these two. And how the calculations were made, they are given here. So multiplication of matrices is also possible. Another important operation is matrix inversion. An inverse matrix is the one which, when multiplied by the original matrix, yields an identity matrix. That is, A multiplied by A inverse is equal to I. Only square matrices can be inverted. For example, we have a diagonal matrix here, B. R, everything except diagonal is 0. So its inverse is very simple. We just take reciprocal of the diagonal elements, and this gives b minus 1, b inverse. So 3 is 1 over 3, 4 is 1 over 4, 18 is 1 over 18. Inversion of a 2 into 2 matrix, it needs a little bit more effort. We need to calculate determinant by subtracting the product of two diagonal elements from the product of two off diagonal elements. Then we reverse the two, and then we reverse the two diagonal elements. We have placed 4 in place of 8 and 8 in place of 4. We have reversed their positions and then multiplied the off diagonal elements by minus 1. So minus 4 and minus 6, and then divide all elements by determinant. So this gives us zero point 0.5 minus zero point 0.5 minus 0.75 and 1. So this is the procedure of taking inverse of a 2 into 2 matrices. Once the order becomes high, it is very difficult to take inversion of a matrix, and we use computers for this purpose. Rank of a matrix, it is the number of linearly independent rows or columns in a matrix. A full rank matrix is a square matrix with its rank equal to the number of rows and columns. And if this is not the case, then it is called a matrix not of full rank. Its determinant is 0, and a unique inverse of that matrix does not exist. For example, we have three linear equations. We have transformed them in the form of matrices, matrices of coefficients, and then x1, x2, x3, and y1, y2, y3. You see that the third row is addition of the row 1 and 2. 3 plus 4 is 7, 2 plus 3 is 5, 1 plus 0 is 1. So this is not a full rank matrix. Its rank would be 2, because third row is dependent on row 1 and 2. This is called another name is called singular matrix. A matrix with its determinant equal to 0 is called singular matrix. It does not have a unique inverse, and a generalized inverse of such matrix is possible. For example, we have a D matrix and we need to get a generalized inverse D minus, which can be calculated by satisfying the expression D minus into D multiplied by D minus multiplied by D is equal to D. So a square matrix with determinant equal to non-zero is called non-singular matrix. It does have a unique inverse. How to get trace of a matrix? Trace is only defined for square matrices. It is sum of diagonal elements of a square matrix. For example, we have a square matrix here. It's 4 into 4 matrix. So we have 1, 2, 5, minus 1. So trace of A is equal to A11 plus A22 plus A33 plus A44, and this comes out to 7. Another important concept is eigenvalues and eigenvectors. So I will not go in details. I will just give you procedures. First, we need to compute the determinant of A minus lambda I. And then we will find the roots of this polynomial by equating A minus lambda I equal to 0. And once we have found out that for each eigenvalue lambda, we will solve A minus lambda I into x is equal to 0 to find an eigenvector of x. So lambda values will be eigenvalues and x would be the eigenvector. So I have taken a lot of things from Murad 2005, and this is a good book. There is an appendix on linear algebra matrices and linear algebra here. We have a full-fledged book of serial 1982, Searle, its matrices algebra useful for statistics. You should certainly read these books if you want details. And I have accessed this website also for information. Thank you very much for your attention.